I'm Noah Kern. As was presented, I work with the Real-Time Computing Lab at the University of Michigan, and this work was conducted while I was a research intern with Lear Corporation this past summer. So today in this talk, I'll be presenting our work in progress of a low-cost vehicle augmentation for improving the safety of vulnerable road users. Okay, so to motivate this talk, we're first going to address a problem called dooring. And so dooring is the road accident vehicle type when a vehicle passenger basically opens the door into the path of a vulnerable road user. So this could be a bicyclist, somebody on e-scooter, runners. I think the GIF gets a pretty good sense of what actually goes on with dooring. Unfortunately, it's still a highly pervasive accident with a pretty high injury rate. About one dooring accident happens per day in Chicago, and over 80% of the accidents that leave bikers seriously injured in San Francisco. So there's several state-of-the-art solutions for dooring prevention, and they all kind of come with their own limitations. For instance, some of them are prohibitively expensive, like the LiDAR solutions. Others have line-of-sight issues, such as with cameras and radars. Vulnerable road users may be required to opt into some of the solutions, such as vehicle to pedestrian or pairing BLE devices. And others are just pretty impractical. I think this picture gets a pretty good sense of why that might be. So we first note that most vulnerable road users today carry mobile devices on them. And so these mobile devices will passively transmit Bluetooth low energy advertising packets. And secondly, modern vehicles have several Bluetooth transceivers that are equipped throughout the vehicle. And so leveraging these 2 points, we introduce a concept called S-Store. And it's a firmware update that we can apply to vehicles that will use these Bluetooth transceivers throughout the vehicle in order to receive passive AD packets from the Bluetooth devices of pedestrians in order to leverage the received signal strength of these packets and the angle of arrival of the packets as well in order to localize these vulnerable road users in a passive way without having to pair Bluetooth devices. Okay, so the primary challenge for accomplishing this task is due to the seemingly inaccurate measurements that are coming from the received signal strength and the angle of arrival. So in order to localize, we may use triangulation or trilateration, but these require precise direction and distance estimates in order to actually, make use of them. And furthermore, these techniques are often used in settings where the objects of interest are lying within the bounds of receivers, but in our case, it's actually outside. And so that means that there are multiple possible solutions, even when the directions and the distance are precise. And so this leads us to a novel algorithm that we propose as part of S-Store, which we call tri-squared, triangulation, trilateration. The first step is for tri-squared to use the estimated distance and direction of these the RSSI and the angle of arrival in order to create these circle sectors and rectangles. And then we'll overlap these in order to create actual pentagons, and then create an arbitrary polygon as an overlap of each of the separate pentagons together. And then finally, we'll find some weighted center of this arbitrary polygon in order to locate where the vulnerable road user might be in relation to the actual vehicle. And so as part of our early tests and experiments, we ran 10 trials for each vulnerable road user scenario of walking, running, and biking. And from these trials, we find that S-Store has a pretty high true positive rate of 100%, meaning that all instances of a nearby vulnerable road user are accurately detected. But we find that as a preliminary downside, that there's still many false positives with this technique. And so a vulnerable road user essentially is being misidentified of being nearby the vehicle or behind the vehicle when neither of these one of these two conditions isn't actually being met. And we also have a image here of the prototype of S-Store. And what we did is we put this prototype on the top of of some stationary car in order to perform these trials. So to conclude this talk, there's some remaining work that still needs to be accomplished to really see a final solution here. The first is that we need a thorough evaluation of the angle of arrival transmission capabilities from smartphones. And second, we need to implement SDOR within the embedded devices of a real vehicle. Currently, as you can see, it was being developed as a prototype that we placed on top of a vehicle. We should also test this in a more diverse set of environments, such as in city landscapes where we have some of the urban canyon problem that occurs. And finally, we should assess privacy implications of using these 80 packets to locate vulnerable road users. And so we could conduct this through a user study. And if anybody's curious to see more about this paper, you can take a photo of this QR. And to see any other work that we're working on, you can follow these URLs. Thank you, and I'm open for questions.
Have you thought about using other modality, other types of communication or other types of signal to enhance the accuracy?
Yeah, so we talked about this a little bit in the paper, but inside of a real system, this could actually be used to complement other things that are available. So as I mentioned in one of the former slides, some of the state-of-the-art solutions include using LiDAR or using camera vision. And so because of those having their own set of problems, this could be used to either enhance those to see around obstacles or to maybe improve their detection accuracy.
Great, thank you.